At its core, an accelerometer is a sensor that measures acceleration, the rate at which an object's velocity changes over time. In simple terms, it detects movement, whether it's a sudden jolt, a smooth shift in direction, or the pull of gravity itself. Modern wearables primarily use what are known as capacitive accelerometers that rely on that MEMS technology developed in the 1980s and 90s that I mentioned before. Now, there are actually a few different kinds of accelerometers, each with different mechanisms of action, but ultimately serving the same purpose: detecting movement. The type most commonly found in wearables is the capacitive accelerometer, which, as I mentioned, detects motion by measuring changes in capacitance. But there are a couple of other types worth knowing about. Piezoelectric accelerometers work a little differently. Instead of measuring capacitance, they use special materials, things like quartz or ceramic crystals, that generate an electrical charge when subjected to mechanical stress. So when you move, the tiny internal mass inside the accelerometer applies force to these crystals, and they produce a voltage that corresponds to the movement, to the acceleration. Then there are piezoresistive accelerometers, which work by changing their electrical resistance when subjected to mechanical stress. These types of accelerometers are usually found in high-impact applications like crash detection systems in cars, where rapid, forceful movements need to be detected. Again, they're not ideal for wearables because they tend to consume more power and aren't as precise at measuring subtle, continuous movements. So for the kinds of devices we wear on our wrists or clip onto our clothes, capacitive accelerometers are the most common. They're tiny, they're power efficient, and they're sensitive enough to pick up everything from small hand gestures to the impact of a foot hitting the pavement when you're running. But here's the thing: accelerometers alone don't give us the full picture. They're great at detecting linear motion, meaning movement in straight lines, but they don't tell us anything about rotation. If you spin in place without actually moving forward or backward, your accelerometer won't pick up much. This is why wearables also rely on another key sensor, the gyroscope. A gyroscope measures angular velocity, or how fast something is rotating. Think about how your smartphone screen rotates when you turn your device. It's not the accelerometer doing that, it's the gyroscope detecting the change in orientation. In a smartwatch, the gyroscope works alongside the accelerometer to distinguish between different types of movement. So for example, when you swing your arm naturally while walking, the accelerometer detects the up and down motion, while the gyroscope senses the rotation of your wrist. And together, when the signals from these sensors are combined and processed, they allow your device to count steps or differentiate between different kinds of activities and recognize gestures like raising your wrist to check your time. But even with an accelerometer and a gyroscope, there's actually still room for error. That's because gyroscopes suffer from drift. You see, because gyroscopes measure angular velocity rather than absolute position, small errors in measurement accumulate over time, and this results in inaccuracies in motion tracking. So to counteract this, some devices also include another sensor known as a magnetometer, which measures the Earth's magnetic field and provides a reference point for orientation of the gyroscope, helping to reduce errors in motion tracking. Now, when you combine an accelerometer and a gyroscope, and sometimes a magnetometer, you get what's known as an Inertial Measurement Unit, or an IMU. Together, these sensors in an IMU can provide 6 degrees of freedom or 9 degrees of freedom motion tracking, meaning they can track movement in 3 translational directions: the sagittal, frontal, and transverse planes of motion, and 3 rotational directions: roll, pitch, and yaw. Plus, if a magnetometer is included, they can determine absolute orientation relative to the Earth's magnetic field. The IMU is the sensor package at the heart of motion tracking in most wearables these days. That's the technology underpinning when your device tells you to stand up because you've been static too long. They're used to measure your activity levels. They can track a run even without GPS, or detect a fall. They're the core technology behind sleep tracking by measuring your movement when you sleep. And IMU data is often fused with data from other sensors like PPG or photoplethysmography, which is used to measure heart rate for even better accuracy.